All right, let's continue here. The slide number 16 we are in, binary equivalent of decimal numbers. Decimal 0 will have all 0, 4, 0 binary numbers. So we have seen this in the last presentation. Let's move on. So you can represent a number to the power of 2, right? For example, this one 16384 can be represented as 2 to the power of 14. Similarly, you can have each of these numbers can be represented into the power of 2, right? So the reason why we're doing this is how we can convert a decimal number equivalent to, or how do we know that what's a decimal equivalent of a binary number, right? So let's see how we can do that conversion, right? So next few slides or 3 or 4 slides, just try to pay attention and just understand the mechanism, how how that can be done, right? We don't have to do this application wise, or we don't have to do this as an exercise or anything, just to have a knowledge that it's possible that we can convert one binary to a decimal to a binary equivalent, right? So let's go on to the next slide here. So a decimal base 10 number is being represented. For example, base 10, how do you represent that, right? A number like 2485 here, right, can be represented as 2 times 10 to the power of 3, 4 times 10 to the power of 2, 8 times 10 to the power of 1, plus 5 times 10 to the power of 0, right? And now you can also further divide that into this way: 2 times 3, 4 times 100, 8 times, 2 times 1000, 4 times 100, 8 times 10, 5 times 1. That's become 2000 plus 4000 plus 80 plus 5, 400 plus 80 plus 5. That's become 2485, right? So this is how you convert, or see how this how do you represent it in a different way using the power of 10, right? Let's see how we can convert. Our goal is to really convert a decimal number to a binary number, right? So next 3 slides we'll see how that can be done, right? Just as a just as how a decimal number can be represented as a sum of powers of 10 with coefficients in the base 10 alphabet 0 to 9, a decimal number can be represented as sum of powers of 2 with coefficients in the base of 2. Okay, so the decimal number we are going to do is we are going to represent it as sum of powers of 2, right? So let's see how we can do that. So the goal is just to understand how we can convert a decimal number to a binary number, right? Just see the mechanisms, okay? So how do we do that? Find the largest power of 2 that is smaller than the equal or equal to the decimal number. Insert 1 in the binary number for the position equivalent to that power of 2. Subtract that power of 2 from decimal number. Repeat operations 1, 2, 3 until you reach 0. Okay, so just don't get upset if you don't understand it. It's not a big deal. We are going to see that at a high level. We just have to understand the mechanisms here. That's all, right? So the largest power here is, for example, we want to convert 359 to a binary number, right? So the decimal number 359 we want to convert to a binary form. What is binary equivalent to that? How is it represented in a computer, right? So the steps here, as we see in the previous slide, first step is to go ahead and find the largest power of 2 that is smaller than 359. So if you could see that 2 times 8 become 256, right? When it becomes 2 times 9, it's more than 359. So we are just finding the smaller number than 359. The smaller number than 359, but representing in to the power of 8, right? To the power. So to the power of 8 is 256. So if you go to the power of 9, it's become bigger than 359. So we are not going there. So we just taking to the power of 8. 359 minus to the power of 8 is, we know that it's 256. So that is become 103. So we can represent this 359 in another format, saying that 359 equals to the power of 8, which is, we know that 256, but there is a remainder of 1 or 3 to become 359. So we have to add that, right? Plus 1 or 3. Okay, so we're showing it in another way, saying 359 can be represented as to the power of 8 times 1 plus 1 or 3. And now so now you're doing the same operations until you split it with the power of 2, or each one of these bigger numbers, right? So do the same thing for 103 now. Largest power for 2 of 2 that is smaller than 103 is 64 to the power of 6, right? 103 minus 64 become 39. 359 equals to the power of 8 times 2 plus 2 to the power of 6 plus 1 plus 39, right? So we are saying this plus this one is to the power of 6 plus 39 is the balance. Now we have to split this 39, right? So 39 is, the highest number can be represented in 2 power is to the power of 5. So 39 minus 32 becomes 7. Now you are saying that 359 can be represented in this format, right? 3 to the power of 8 plus to the power of times 1 plus to the power of 6 plus the time ones plus to the power of 5 plus 7. So this is how you represent. Now you have to split 7 to the power of 2, right? So to the power of 4 is the highest it can represent. There's a balance of 3. Now you split that again for 3, again to the power of 1. 3 minus 1, there's 1. Now you come up with all the powers of 2, right? So 359 can be represented as to the power of 8 plus times 1 plus to the power of 6 times 1 up to 1, right? So this is how you are splitting that using the power of 2, the decimal number, right? Now, the largest power of 2 that is smaller than or equals to 1 is to the power of 0, right? So 1 minus 1 is, so we are finished here. So in other words, we have done this. There's no more split we can do for this representation here, right? So let's go on and see how we are converting this representation of this decimal number to a binary, right? Look here, our result is 359 equals to the power of 8 times to the power of 7. So this is how it's been represented from the previous slide, right? To the power of 0 to 1, right? Or you just have to remove the powers of 2 we get, right? So if you remove all the powers here, ignore 2, 8, 7, 6, 5, 4, 2. What are you doing is 2 the power 2 times 1 to the power, ignoring or removing the powers here, right? Removing the powers of 2. So just remove all the 2 raised to the power of 8, to the power of 7, to the power of 6. You will have only left with what? 1, 0, 1, 1, 0, 0, 1, 1, 1, right? That's what we are taking to get our decimal equivalent here. So 359 can be represented as 1, 0, 1, 1, 0, 0, 1, 1, 1. It's right here. Okay. So that's how you're converting that decimal number to a binary equivalent, which computer understands, right? Just understand that as possible we can convert, you don't have to, be by heart or worried about, don't understand the nitty-gritty of this. This is how you can represent it this is how it's represented in computer as a decimal number equivalent, right, for a specific number. Okay. Then we have another numbering system called hexadecimal, right? Hexadecimal is another way you can represent numbers. Hexadecimal is a base 16 number system. It uses digits 0 to 9 and A to F. It's plus, you have the binary in this decimal number 0 to 9 plus the letters A to F, so it can have a base 16 number. In appendix 6 you represents all this 12 in decimal numbers. Hexadecimal is digit can represent a decimal value from 0 to 15. Okay, so it's not just 0 to 9. You have A to F also, thus it can be represented a little more wider structure of numbers, right? Thus one hexadecimal digit can represent 4 bits. Okay, so let's see what are some equivalent of binary and hexa digits, right? So digit 0, hexadecimal, or digit 0 represents a binary of 000. Hexa for 1 is binary is equivalent of 001. All that you can see, 3 is here, 4 is here. When it comes to characters, hexadecimal, as we know, 09 plus another 6 more, right? So total of 15 number systems, right? Decimal values, right? So then it can also have A, B, C, D, E, F, which is represented as binary values 1010, 1011, 1100. That's how it's been represented. Okay, so it's another numbering system. Just be aware of that. Binary number equivalent here, again, binary number is 001, and equivalent of that is hexadecimal equivalent is 1. 1010's equivalent is A. 111 equivalent is F. 1001 equivalent of 9. Hexadecimal equivalent. Okay, each one of those numbers. The Unicode character set. So how do we represent characters? We know that number, decimals, binaries, hexadecimals are all represented, but we need to represent the characters A to Z and all that, right, on different international character sets, right? Each character is stored in 16 bits. Okay, characters are stored in 16 bits. Maximum number of characters that can be represented using Unicode character set is 65,536 to the power of 16. Also, you can represent it characters using ASCII, which is American Standard Code for Information Interchange, right? ASCII. That's another way of representing character. Java is using UCS, Unicode character set, right? Other programming languages using ASCII character sets. It's a 7-bit. So difference is Java can represent much more wider characters, like international characters, other foreign country language character sets, right? ASCII represents only 7 bits, so you can have maximum 128 character sets. For compatibility, the first 128 characters, so just for compatibility between these two, ASCII and Unicode character set, the first 128 characters of Unicode set represents the ASCII equivalent. Okay, so if you're taking the first 28 of ASCII and Unicode, those two are the same, for compatibility between computers, different languages, right? So these are the basic Unicode character sets here. Now character is represented in decimal 0, but hexadecimal 0, 0, 0, 0. Star character is represented 42, but in hexadecimal is 0, 0, 2A. 1 is represented as 49. In hexa value 0031, 250, and 0032. A can be represented as 65 to 0041. So just how do you represent Unicode to decimal